All right. So, we are about to embark on really understanding a lot more about molecules, okay? We have a way to predict the bonds. That's our Lewis structures. They really tell us the bonds and unbonding electrons. They sort of tell us where the electrons are. Remember, Lewis structures are what we call a localized electron model. We assume that we can say with specificity where the electrons are, okay? We know that that's not really the best model, but it works really well for a lot of compounds, and it's something that we can do instead of the crazy math to do like a molecular orbital approach that we can't really do. We know that one of the big goals here is we're trying to get a bunch of different colors. We want to dye our yarns. We want to dye our fabrics. A lot of that, how the dye sticks, has to do with its polarity. Well, it turns out that to predict the polarity, we need to understand the shape of the molecules. We've been drawing our Lewis structures in many ways in this very flat, right-angle approach to bonding that doesn't really match reality very well. Okay? It's great for allowing us to sort of quickly put together a molecule and know what's bonded to what and how many lone pairs of electrons. But we need to take it that next step and look at how many bonds, how many lone pairs, and how does that help us understand the actual shape of the molecule. Okay? To do that, we use a process, we use a theory known as VSEPR. Okay? Valence Shell Electron-Pair Repulsion theory. Fundamentally, that mouthful of words is electrons, because they have the same charge, will move as far away from each other as possible. So the geometry of a molecule is based around moving the electron pairs as far away from each other as possible on a three-dimensional sphere. We imagine the atoms are spheres, and we're going to move the electrons as far away from each other as possible. Now, that doesn't jibe real well with a lot of the atomic orbital stuff we learned. And so we're going to fix that mismatch next week. But there is a way that we can sort of fix that mismatch between the atomic orbitals and what we know to be true about molecules. So VSEPR, Valence Shell Electron-Pair Repulsion, does explain the shapes of the molecules pretty well. Okay? It's not the perfect model, but it's really good for the molecules that we want to be able to look at in this class. So we'll have to reconcile those two things in a later lecture. Fundamental to the geometry is the number of electron pairs. Whether they are bonding or lone pairs is in many cases irrelevant. We simply want to know how many pairs of electrons do we need to arrange around the atom. Okay? And then what do we call that? The geometry is the shape of the electron pairs. How are they arranged around the spherical atom? Okay? Key things here, we got to think three-dimensionally. But in many ways, this is simply count up the number of electron pairs, how many are bonding, how many are non-bonding. That's the shape. Okay? So, the simplest case, I have two pairs of electrons. I have two pairs of electrons that I want to maximize their distance around a central atom. Okay? So, we're going to use some models to do this. And so I have a set of models up here that I like to use for this. And we're going to use sticks to represent electron pairs. When they're connecting two atoms, we call them bonds. When they're not connected to two atoms, we call them lone pairs, when it's just stuck on one thing, right? So regardless, if I have two items and I want to put them as far away from each other as possible around a sphere, what is that arrangement? 180 degrees, a line. Okay? So the arrangement is a line. Okay? Those two things can be at most 180 degrees. Okay? We call that geometry linear. Comes from line. So here's my linear geometry. That's the best way to arrange two things that want to repel each other from make them apart. 180 degrees angle. Okay? Linear geometry. Now, what if I have three things? If I have three things that I want to arrange around my central atom. Sorry. Got to grab some sticks here. So, if I have three things that I want to arrange, I can maximize their distance. The best thing I can do is get them 120 degrees from each other. Okay? This sort of geometry is the maximum distance that you can have three things. They form a flat plane. Okay? And that is trigonal, because it forms a triangle, and it's planar because they all lie in a flat plane. So trigonal planar is a geometry for three things that you want to arrange around a central atom. Okay? What if I have four things that I want to arrange around a central atom? This is where we leave the realm of the familiar in many cases. Okay? You may not be used to this shape, but it is extremely important. Many atoms take on this configuration because 4 pairs of electrons is how many electrons? 8. That's our octet rule. So a lot of things are going to have pairs of electrons arranged with 4 things arranged at a maximal distance from each other. Okay? This 4 things arranged around is what we call tetrahedral. This is a tetrahedral geometry. Okay? You have 1 straight up, 3 pointing slightly down. This is an angle of 109.5 degrees. 109.5 degrees. Questions?
When you draw them, like if you were like writing it down, would you have it to look like a plus sign?
So typically if you were to draw this for a Lewis structure, you would have them at right angles to each other. That would be very typical, and that's fine. Lewis structures are not geometries. But you need to know how to interpret that Lewis structure. If I give you a molecule like methane, CH4, and you draw 4 single bonds around the carbon, you might draw them at right angles. That's totally appropriate. But you need to be able to tell me the geometry is tetrahedral, and the bond angle is 109.5. By and large, what you need to know is how it changes when you have to deal with lone pairs versus bonding pairs. So, yeah, there are certain angles. This one is an important one, 109.5. That's not super important, but it is good to know. Questions?
For linear and trigonal planar, those are the only 2 that are 2 different.
Yes, the rest are, well, it's a little more complex than this first pass. This is the way that the electrons will be arranged. When we start to talk about molecules, we only look at the bonds. But the lone pairs change the shape and are important, but we name them based on the bonds. So some of the molecules will be planar that, because of the way the lone pairs are arranged. We'll get there. Yeah.
So does it matter how it looks on a Lewis structure?
No. Fundamentally, Lewis structures do not tell us geometry. They're not intended to, but they help us understand and get to the geometries by telling us how many lone pairs and how many bonds. Okay? All right, so we've got 2, 3, 4. Of course, we need to think about 5. If I have 5 pairs, do I have 5 more yellow sticks? Let's see. 1, 2. Because I like to be able to go back and forth a little bit. Yeah. So, 5. This one's messed up. Yeah, some of the other teachers. Not me, of course. So, 5 things arranged around a central atom. The best arrangement, the lowest energy, the greatest distance is what we call this shape. Okay? I have 3 in a flat plane. Okay? 3 of them in a flat plane, 1 above and 1 below. And we call this trigonal for the flat triangular plane, bipyramidal. two pyramids. We have a triangular-based pyramid on the top and a triangular-based pyramid on the bottom. Okay? Trigonal, bipyramidal. Carefully. It's hard to draw. These three-dimensional shapes, I'm not going to deny it, they can be difficult to draw. There are some other notations that you start to use when you go more advanced into this stuff, where you have wedge-shaped bonds that help give a sense of depth. You just do the best you can. Okay? Mostly people are going to ask you names. They're going to say, draw the Lewis structure and tell me what the geometry is. Okay?
Mr. Fleming, what's the Lewis structure of that?
The Lewis structure for that would be something like phosphorus pentachloride.
No, I mean like, how would you draw it?
You have 5 chlorines around a phosphorus. Yeah, 5 things around the central atom. 5 pairs of electrons around the central atom. That includes lone pairs or bonds. But an example that you've done is phosphorus pentachloride. That is an example of this one. Okay? And finally, the last one, if we have 6 pairs of electrons, I am going to have to reuse this one here. It's got, why is what? Yeah, the world is a crazy place. So in this one, we have 4 in a flat plane, 4 pairs of electrons in a flat plane, one above and below. And no, this is not square bipyramidal. It has a different name called octahedral. This is an octahedral shape. Yes?
I was just wondering, in the picture of the arrangement of electron pairs, next to each line there's 2 electrons. Why is there like 2 electrons at the end of each line?
We're talking about lone pairs. We're just arranging electrons.
Can it also be an atom?
It could, and we're going to go into that in just a sec. A couple minutes.
What if it was something like N2, N2?
So all of this geometry stuff is predicated on having one central atom with other things arranged around it. You talk about the geometry around an atom. You don't talk about the geometry of a more complex molecule. So you talk about the geometry around this atom. This atom has a tetrahedral geometry. This atom has a octahedral geometry, as this one does. Okay? Yeah, right? Because I could just take, I could take this and stick it on here like that. So now this one has got trigonal planar, but this one is octahedral. But typically you name the shapes based on the actual atoms, okay? And this is where this octahedral stuff, this is where it's going to get a little tricky. This is the way that the atoms themselves, this is the way that the electron pairs are arranged, right? But we're going to name things based on the molecules, okay? So what we want to know is how many electron pairs do we have? How many are bonding pairs? How many are lone pairs? Then we'll go ahead and be able to put on here, for those electron pairs, we'll be able to go ahead and put on how many are bonding pairs, how many are non-bonding or lone pairs. Then we'll be able to talk about the arrangement and finally the name of the shape. Okay? So we're going back to our original idea. Did I take that one apart too? Oh, it was this one. Sorry. So our simple idea, 2 pairs of electrons. Okay, 2 pairs of electrons. Both are bonding. What does that mean for this model? It means stick something on the end. So these now are bonds. I have 2 bonds, okay, to 2 different atoms. I have no lone pairs.
How do you get lone?
Lone pairs are when you put the 2 dots on something. When you're building your Lewis structure and you have 2 dots, that's what we call a lone pair, a non-bonding pair of electrons, because it's not bonded. So arrangement, exactly the same as before. Geometry, exactly the same as before. This is linear. Okay? Now, we can get a little more complex. We can go up to 3, right? So I can have 3 pairs of electrons. So we go back to our 3 pairs of electrons, and I'm going to have 3 bonding pairs and no lone pairs. Okay? So here's my 3 bonding pairs and no lone pairs. And that's the same as it was before. This is my trigonal planar geometry. 3 bonding pairs, no lone pairs. Now, what if instead of having 3 bonds and no lone pairs, I could have 2 bonds and 1 lone pair? Okay? So now, in this case, the electrons are still arranged in that trigonal planar shape, but the molecule is not. The molecule is named based on the atoms. Okay? So I have this lone pair of electrons on the top, right? So the shape, those don't count in naming the shape. They drive the shape and they're important in the shape, but they're not named as part of the shape. So we're going to call this bent or V-shaped.
When you have a molecule that has non-bonded pairs and bonded pairs, so that angle is different between...
So this is an important point. Lone pair electrons, non-bonded pairs of electrons, are only attracted to one atom. So their orbitals tend to be larger. They take up more space and tend to compress the bonding pairs together. So instead of being 120 degrees, this is going to be a little bit less than 120 degrees because this lone pair takes up more space, repels the bonding pairs a little bit. It depends exactly on what atoms are involved because they're going to have different protons and things like that. And actually 120 is far enough away that it really doesn't have much of an impact. It's when we start to look at the tetrahedral geometry that we really start to see a change. Questions?
Did you say bent trigonal planar?
Nope. Bent. Just
It
bent.
could be anything. Because like for the fourth one, it's also bent.
Right. We don't care because the geometry is just how are the atoms arranged. These atoms are arranged in a bent conformation. They're bent geometry. If I have 2 atoms, what's the only way they can be arranged no matter how many electrons they have? Yep. If I have 2 atoms, it's always linear. So we never have to worry about that. If you only have 2 atoms involved, you can only have a line. 2 points can only form a line.
But if you have an unbonded pair,
Doesn't matter. Doesn't matter how many unbonded pairs you have, because if you only have 2 atoms, you can only connect them with a straight line.
okay.
Nothing else matters.
Oh, I get that.
Okay? So now we can go on to our 4. So here's my 4. This is my tetrahedral geometry, right? So I have 1 central atom, and I have 4 other atoms bonded to that with no lone pairs. I've got my tetrahedral geometry. Okay? And that's tetrahedral. That's 4 bonds, no lone pairs. That's my tetrahedral shape. What's the angle here? 109.5. 109.5. Okay? That's the best angle that you can get for 4 things arranged around a sphere.
And do all the angles add up to like the same fixed amount?
I don't know.
Okay.
Well, isn't it?
I don't think so.
Well, yeah. I mean, if it's a sphere and you divide the angle, that's too bad.
I don't know. I don't know. That
So I was just like thinking
maybe.
there's triangles.
All right. So 4 bonds, 0 lone pairs. Okay. We have. What if we change it? What if we go to 3 bonds and 1 lone pair? Okay. 3 bonds and 1 lone pair. So we have a triangular-based pyramid, okay? And we call that trigonal pyramidal. This is like ammonia. This is ammonia is a good example of this, right? NH3, we've got 1 lone pair on the nitrogen. This lone pair takes up more space. It pushes these bonds down, pushes them closer together. So instead of the 109.5, you get something like a 107.5. So this is about 107.
If that was on a test, would we say?
Mostly on the test, what you need to be able to say is it is less than 109 because the lone pairs take up space. All right? Now, I can pop another one of these guys off, right? Now I'll have 2 bonds and 2 lone pairs. Okay, 2 bonds and 2 lone pairs. This is water. This is a water molecule, right? This is bent or V-shaped, but bent. Again, now I have 2 lone pairs pushing these down together, so they get pushed even a little bit more. This is down to about 104, 104.5 for water. Again, it changes a little bit depending on exactly what atoms you're talking about. For water, you're looking at about 104. So 2 lone pairs push these together even more. They take up more space, squish these guys down together a little bit.
Do the 2 lone pairs have to be arranged like in a 3-dimensional way?
Yeah, remember, think back to the first thing I taught you. 4 pairs of electrons, they're going to be tetrahedral. I'm using the same atom, 1, 2, 3, 4, basically tetrahedral shape. But we name the shape of the molecule based on these actual atoms that are involved. The lone pairs drive the shape. The pairs of electrons drive the shape. The name comes from the actual atoms. Okay? Now what if I go to 5? Why do I not need to go down one more? What happens if I only have 2 atoms? It's always linear. If you have 2 atoms, there's nothing you can have but linear. All right, so 5. Here's my 5. So remember those lone pairs taking up more space? That turns out to be important in a lot of ways. So here's my 5. This is 5 bond pairs. This is exactly like 5 electron pairs. We're going to have our trigonal bipyramidal shape. Okay? My trigonal bipyramidal shape, right? So if we, let's get that board out of the way there. And we'll go to the 5. Now what if I pop one of these guys off? Okay? So here's the thing. There are 2 very different spots in this molecule. I have this axial spot where they're above and below, and I have this plane, this flat plane here. Okay? Lone pairs take up more space, and the system is going to minimize that repulsion, right? So if I have lone pairs in this kind of structure, they're going to go on this axial plane first. They're going to go in one of these 3 in the axial plane because they have better angles, okay? Greater angles. If this atom, this bond, this pair of electron is at 90 degrees to 3 different pairs of electrons, whereas this axial position is at 90 degrees to only 2. 90 degrees is really close for a pair of electrons. So the lone pairs, which are larger, are going to come off of that equatorial position first. Okay? So you got to keep that in mind when you're doing 5. Okay? When you're dealing with this trigonal bipyramidal structure, the lone pairs come off of here first. Okay? So 4 bonds, 1 lone pair, looks like this. Okay? Does this look like anybody's favorite common childhood playground equipment? Yes. This is a seesaw shape. Okay? Seesaw is the name of the shape. Apparently, chemists have a sense of humor too.
Did you say that in Russia? Like,
I have no idea what they say in Russia. I don't know. I know that seesaw is what they'll accept on the AP and IB tests. I'm assuming a seesaw is a familiar child's toy all over the world, since all you really need is like a rock or a log and a board.
oh, but are these standard names? For
These are the standard names that everybody uses that I know of. I'd have to double check the IUPAC names, but I think these are IUPAC names. All right, so now I'm going to take another one off. What if I have 3 bonds? Where should I take the next one off? Another equatorial one's going to come off. Okay?
Why do you call it equatorial instead of plane?
Because it's the middle.
It's on the equator. instead of like if you imagine it spinning like this. Although, yeah, that's. Yeah, these things all spin in space in lots of different ways. And they vibrate and wiggle. The bonds aren't hard. They're more like little springs. Yeah. All right, so again, now I have 2 lone pairs. Okay, I've got my 2 lone pairs here, and I've got 3 atoms. Does this look like a common letter of the alphabet?
T.
Yeah, this is T-shaped. This is T-shaped. Okay. Now, what if I take one more equatorial one off? Oh my gosh, we're back to linear. Okay, 2 bonds, 3 lone pairs. We're back to a linear molecule. Okay? All right, the last one. We'll go for the octahedron. Huh? No, we're going to do 6. It's 8 sides. It's 8 faces. It's an octahedral solid. Not under any kind of normal conditions that we're going to experience. Yeah, Eden. Shh. I'm sorry, the trigonal planar one? So if you have trigonal planar like this, and you have 2 bonds and 1 lone pair. So this, yeah, well, mostly because the best way to arrange 3 things is in this trigonal planar shape. And we call it bent because we name based on these atoms. Now, when we were dealing with the other one, remember that the best arrangement had 3 in the equatorial plane and 1 above and below. We took the 3 in the equatorial plane, then we have the above and the below. And the 3 in the plane push evenly top and bottom to keep those straight.
Is the most, well, what's the most number of, the highest number of electrons that a molecule can have, like, its highest energy?
So for our purposes, 12 is about the highest. That's the highest you're ever going to say. That's why we're only going to the 6 bonds. Yeah. Does other stuff, crazy stuff happen in the universe? Yeah. But for our purposes, we're going to stick with 12.
Okay.
Okay?
What would you call something like that if it was connected to another one of those?
Typically, you talk about this atom. So like if I had it, you know, this stuff absolutely happens in real life, right? Where you would have something like this. Right? Well, I say the geometry on this atom, is octahedral. The geometry over here is trigonal planar. So I talk about the geometry about one of the atoms. I can't talk about the geometry, or bent. Well, no, this would be trigonal planar because it's connected to this thing here. Yeah.
So do these shapes apply to like organic chemistry? Carbon normally forms chains.
Yeah, organic the longer the chain gets, the less you worry about these specific things. So carbons are all going to be basically tetrahedral. The other thing that happens is double bonds. Double bonds count as 1. Double bond counts as 1 bond because of the way they form. We'll talk about that in a sec. All right?
What atoms or elements form have 12?
Elements on the 3rd period and lower can go up to 12. Phosphorus, sulfur, chlorine, selenium, bromine, iodine, those are the common ones we see.
When they form like rings, are they like rings of that? Or is it just like you know, like those what are they, I don't remember, halo.
Yeah, I mean like the benzene ring. Yeah, we'll look at that tomorrow. Let's do that tomorrow. But yeah, they just form rings. I mean, it's not they're nothing crazy. No. I mean, for our purposes, right? The universe is a strange and wondrous place. All right, 5 bonds, 1 lone pair. Okay, 5 bonds and 1 lone pair, and we have a. Again, it's like a pyramidal structure. In this case, it's a square pyramidal because we have a square-based pyramid. Sorry. Attacked by a hydrogen atom.
By a square pyramid.
when hydrogen atoms attack. All right, so we can pop one more of these guys off. Again, to minimize repulsion, the lone pairs want to be further away from each other, so they're not going to be next to each other. The lone pairs at 90 degrees is going to be bad energy, going to be a lot of repulsion. Bad magumbo. All right, so 2 bonds, 2 lone pairs, 4 bonds. We're going to have the lone pairs top and bottom, and we're going to have square planar. We're going to have square planar. So if you had it like this, so if you had them like this, now my lone pairs are 90 degrees from each other. And that's a lot of repulsion. That's way too close for lone pairs. It's lower in energy, lower overall repulsive forces if the lone pairs are opposite from each other. Okay? All right. Fundamentally, that's all that we need to know. Okay? We're only going to have to deal with the octahedrals that have 2 lone pairs at most. Most of the molecules aren't going to do more complex things than that. So here's what I'd like you to do. Take out your example. Okay? Give me the Lewis structure for ammonia and tell me its geometry. Oh.
No, it's not.
Okay, so we know how to do this, right? I'll do this one. I'll go through this one, right? We know the nitrogen, 5 electrons. We put the nitrogen in the middle. We do hydrogens around it. Single bonds to each of the hydrogens. We have 2 electrons left. That goes on the lone pair. Okay? What's the geometry here? That's going to be trigonal pyramidal, right? That's the electrons. The electrons are arranged tetrahedral, in a tetrahedral geometry, but the atoms, because I only have 3 of them, the atoms are arranged in a trigonal pyramidal shape. Lone pair, 3 bonds, trigonal pyramidal. Okay? All right. Do these 2 for me. Do water and do H2CO. Yeah, hydrogens can never be the central, so oxygen's going to be the central. Of course. Grab the pass. It should be on the card here someplace. All right.
Should we draw 3D?
No, what I would do is do your Lewis structure like normal, because all I'm asking you to do is draw the Lewis structure, and then look at the number of bonds and the number of lone pairs, and tell me the shape. You can start to draw your Lewis structures in a more representative form, if that helps you, but don't feel like you have to. Yes, we can do it. Right? You've got your oxygen, single bonds to each of the hydrogens, and we have 2 lone pairs on the water molecule, right? So 2 lone pairs, 2 bonds. What's the geometry? Bent, right? So remember, we have those lone pairs on there. I'm using red to indicate these lone pairs, but in reality, we name it as if they're not there. They drive the shape, but we name this bent because of the atoms. Okay? So lone pairs are there. They make the geometry what it is, but we name based on the atoms. All right, so now we got our next one. We've got carbon. Do a single bond to each of the hydrogens. And what do we got to do with the oxygen? We got a double bond to the oxygen. Okay? And then the oxygen does have some lone pairs on it, right? But those lone pairs on the oxygen don't affect the geometry of the actual molecule. They're not going to drive the geometry of this molecule here, right? So notice I have these nice springy double bonds. Okay? Because of the way they form, they count as one, because they only drive one connection. Okay? So a bond of a double or a triple bond only counts as one because of the way they form.
This is bent too.
So this is trigonal planar. Trigonal planar. Look at the central atom. How many? 1, 2, 3 bonds. And look at it, right? When you look at the model, this is all in a flat plane, trigonal planar. The lone pairs on the oxygen don't do anything. They don't drive the geometry of the molecule. Look at the central atom. Okay? So trigonal planar. Okay? All right. We got to nail this molecular shape stuff down cold, because we're going to need it for a very important piece of doing polarity, which is our sort of one of our big goals here, is to be able to get to this polarity stuff, because that drives a lot of important molecular properties. Questions?
Well, I was just thinking, so the molecular geometry of something, if the oxygen atom had more electrons, would it make the angles get wider?
It's not really going to change this angle, the electron pairs here, because it's not going to affect these ones, the ones down here on the central atom. These lone pairs are too far away to push these guys out of the way. Okay? There are chemical properties that are affected by that, but nothing that we need to worry about by and large.